Because I'm pretty sure we completed processes, right? Pretty sure we did all. So. Share state transitions. Yep, we talked about the context switch and why it is necessary. Although, so a little bit of clarification. Understand that the context switch happens anytime the CPU is interrupted and we have to move into privileged mode or administrative mode. So, but from here on out, and including when we talk about concurrency, context switch kind of becomes synonymous with swapping processors, swapping threads. Okay? It is true that switching processes involves a context switch, but that's not all a context switch is. It is literally going from user mode to privileged mode and back again. And I'm not 100% sure if I need Zoom today. I'll go ahead and get it started regardless. Oh, something that I didn't mention first day of class. So occasionally, due to illness or life circumstances or whatever, I'm not able to come in campus. It doesn't happen very often, but it does happen. In those instances, I will try to give you as much advanced warning as I possibly can with switching to Zoom. All right, so no one's connected. So just know that just because I don't host the class remotely for you guys to attend remotely or record sessions, that doesn't mean that Zoom isn't an option. It is an option if circumstances call. All right, we talked about the cooperative approach. And the cooperative approach, as review, each process determines when they're on or off the CPU through the yield system call. And the non-cooperative approach. So the non-cooperative approach, one, we need the help from the hardware by way of the timer. The timer fires off the timer interrupt. When the CPU sees that the timer interrupt is set, it then transfers control over to the operating system, and then the operating system is allowed to do stuff, like in this case, as we've seen, perform a context switch. All right? So yeah, we did cover everything. So smooth context switching makes each process think it has its own CPU, and the reason that it works is because we have perfect safe states. So everything that a process needs that's part of its runtime state is saved and then restored. So that is what makes a process, and it's not so much that the process thinks it has its own CPU, it's that the process does not need to be aware, has no need to understand that it is sharing the system with other processes. This is what we mean by transparency. And I know we normally think of transparency as being able to see through things, but in this use of transparency, what we're basically saying is the opposite. Processes cannot see what the operating system is doing and do not understand their own state as a result and have no need to. Direct execution makes processes fast, but it's also dangerous because direct execution also implies that total control over the hardware. So we need limited direct execution where we allow processes to spend a as governed by the operating system. So hardware provides a lot of operating system support, so limited direct execution through interrupts such as the timer system calls and that sort of thing, timer interrupts, and automatic register savings. This is huge because it is the registers. That's the bulk of a process state. What are the values in the register at any given moment? What's the process working on? All right, and then today we'll cover CPU sharing, policies, scheduling, etc. Any questions about last week's lecture? Y'all tracking? Y'all good? All right. So, all right, schedulers, chapter 7 in your text. We're going to talk about workloads, schedulers, and metrics. In other words, what are the things we need to consider when we talk about scheduling processes on the CPU? We might get, I'm pretty sure we'll get to MLFQ, that's multi-level feedback queue. And I'm almost certain that we will not be talking much at all about lottery scheduling. So mostly chapter 7 and 8. All right, so we've talked about what processes are. And by quick review, a process is a program that has had life breathed into it by the operating system. And by that, I mean that code and data that sits on disk gets loaded into memory and pointed to by the operating system, going on. All right, we will be talking about the heap and the stack all throughout this class. So a process in memory is code, the stack, the heap, and in some cases, global data, static data, that can be a separate area as well. State transitions, and this is a big deal. All right, you need to get this down. So, a process can only transition between states as described in this diagram. In other words, all right, let's start with ready, because all processes start, they're initialized in ready mode, which means that they're on the process queue waiting to be put on the CPU. When the CPU, or when the operating system decides that it's time for it to go, it gets scheduled and it transitions from ready to running. And you'll notice something here in this diagram. There's only one path to running, and it's from the ready state. Meaning that if there are any intervening transitions or states, you ultimately have to get passed back to ready. So when you're running, there's pretty much two things that can happen to a process. One, the process is killed because you've exited the application, the program did what it needed to do, or it encountered an error, in which case it is marked as terminated, and the operating system then cleans it up, frees up its memory, etc. The other state that you can go into from running, actually, I take that back, there's three states. The operating system can choose to deschedule a process, or take it off the CPU, in which case it goes back to ready. And the only way that it can go from ready back to running is if the operating system says it's okay for you to go. The other option is it can go into a queue. In this case, we call it block. You can consider it sleeping. I will frequently use block or sleeping interchangeably, but know that it's the same thing. In essence, the process is taken off the CPU and put on a special queue awaiting some external agent to quote-unquote wake it up. Or, in reality, put it back into ready mode so that it can get scheduled for execution. So, you go from running to blocked. Most common case for blocking would be if you make an I/O request, and you don't want to sit there and hold forever for the device. You know what? I know the device is going to take a while. Let me go take a nap, and just let me know when it's done. And so the process goes into the blocked queue, and then when the device is ready, has the data, the request completes, then the process is taken from the blocked queue, placed into the ready queue for scheduling by the CPU. Implication, very important implication. This means that no process is allowed to immediately run. No process is allowed to immediately run. All processes, before they get put on the CPU, must first go into the queue. That means that there are potentially other processes waiting in line in front of it. So it may be a while before you actually get to run. All right, how to transition, that's the mechanism, that's the context switch. When to transition, that's the policy which we'll talk about today. All right, so when we talk about the context switch, what are we talking about? This is the struct under XV6. There's a little bit more to it than that under full fat Linux, but these are the basics, and this is just so that you understand there's a whole bunch of stuff that needs to get saved, that needs to get tracked per process for a context switch. All right? We care about the context and the KStack. The KStack is actually what enables the hardware saving and restoring of the registers. And of course, we have this diagram, yet again, that walks us through the process of the context switch. All right. So, we're going to look at schedulers, or at least these three basic schedulers, with these three attributes. The workload, the scheduler, and the metronome. And this is true, by the way, generally speaking, it's true for pretty much any area of computing where you are concerned about performance and correctness. So what are we talking about here? The workload is the set of job descriptions. In other words, what processes are currently running or scheduled to be run, and what's their nature, how long will they run? Asterisk, asterisk, asterisk. We'll get back to that, because that's a little bit misleading for now. The scheduler is just the name of the policy. What algorithm are we going to use to choose between processes and when they run? And the metric is what's important. We're going to look at several metrics. The metric is really, it's your objective truth. What is the effect of this policy in the context of this workload? And that's really important, because, and this is true in the world of benchmarking in general, where somebody can tell you, man, I just ran this benchmark, it's really, really, really fast. I'm really happy with my system. Okay, and they give you like some numbers. And then you turn around on your system and you try to run the same benchmark, and you get a much lower number. Why? Well, what was the workload? What were you actually benchmarking? What was going on in the background? What were the circumstances of the benchmark? All of that matters. All right, so we can look at all of this in this abstract form as a function. Our metric, our performance, is the function of the workload and the schedule. We're going to start with a series of assumptions, because we like to start from baby's first algorithm. And we make a bunch of unrealistic assumptions just to kind of get a handle on the algorithms themselves. So, 4 totally unrealistic assumptions. 1, each job runs for the same amount of time. We know that's not true in real life. All jobs arrive at the same time. Well, isn't that convenient? All jobs only use the CPU and do not perform I/O. That's also convenient because we don't have to then consider external unknowns. And the runtime of each job is known. This is the hardest, for our evaluation of our first three algorithms, that's the toughest one to break. All right, so we're going to be looking at workloads in terms of arrival time and runtime. So all we care about each process is when they get to the system, when they get into the queue, not when they run, but when they are loaded and they are put on a queue, and how long they're going to run. We're going to be looking at, oops, I've been saying we're at four schedulers. FIFO, SJF, which is shortest job first, SPCF, shortest time of completion first, and RR for round robin. And the metrics that we care about are turnaround time, which is the time that a process comes into the queue to the time that it exits. And the response time, which is the time that a process enters the queue and the time that it is first scheduled on the CPU. All right, so we look at FIFO, and in reality, processes don't ever arrive at the same time, but we're going to pretend for now. Even though, like here, the arrival times are like down to, what is it, milliseconds? So, we have jobs A, B, and C, and they all arrive at the same time. For our purposes, the arrival time is 0, and they run for 10 seconds each. Well, with FIFO, we're going to pretend that they came in alphabetical order. So A runs first, and B runs first, and C runs first. Our turnaround is the final completion time minus the arrival time. And like I said, we're going to approximate these effectively to 0. This is what it looks like. So A, B, and C arrive at time 0. They're all put in the queue. We're going to run them in alphabetical order for convenience sake. So A runs first, and then A completes at time 10. Then B runs, completes, C runs, completes. So they all run in sequential order. And this is what it looks like in a quick visualization. No surprises here. So, what is the average turnaround time? And there were handouts that went with this, but I skipped them. So let's go ahead and work this out. What's the average turnaround time? All right, A came in at 0 and left at 10. So its turnaround time is 10. B came in at 0 and left at 20. Its turnaround time is 20. C came in at 0 and left at 30. Its turnaround time is 30. So you can see that B's got a little bit of a problem because its turnaround time is pretty long in comparison with the rest. 10 plus 20 plus 30, that gives us 60. We divide that by 3, and our average turnaround time is 20, which is twice the length of the runtime of each individual process. So, not great. So, we have a problem where running them sequentially as they are, it's not optimal. Can we do that? All right, so our workload assumptions. Let's not assume that each job runs for the same amount of time. Let's have variable length run times. All right. So The example here, big first job. So under FIFO, A runs for 60. So we already know, we've already got a problem because that's going to yield a turnaround time that is huge for B and C. It's going to be what? 60 plus 70, 130. 130 plus 80 is 210. 210 divided by 3 is 70. So one big process under first in, first out, and our metrics completely tank. Because B and C have to wait all that time for A to complete. This is called the convoy effect. You guys know this firsthand, driving into campus and getting stuck behind the school bus. That's this. One long, slow job holding all of the smaller ones back. All right, so can we fix this? What if we said, what if we prioritized shortest jobs? Get them out the gate quicker. So we have shortest job first. When deciding what job to run next, you take a look at the queue, take a look at the run times of the processes in the queue, and always pick the first one. Or the shortest one, I should say, not the first one. All right, so in this case, here we have 60, 10, 10. For convenience sake, we're going to pick B because it's a tie between B and C. So we'll pick B. B gets to run first. Once B is done, then it's between A and C. Well, that's easy. Pick C. So now C runs, and then A has the CPU all to itself thereafter. So in this case, we went from 70 seconds turnaround time to 36.7. So it's a marked improvement over the prior. So, can we remove another assumption to make the problem a little harder? All jobs don't arrive at the same time. All right, shortest job first, arrival time. Notice that we're back to where we started. Process A, 60, it happened to get there first by all of 10 seconds, but it got there first, and so B and C still have to wait. So the average turnaround time in this case is we're almost at that 70 mark, 63.3 seconds in this case. So we still have a problem. So here's what we might need to do. In fact, did I give enough of a spoiler? I think I gave enough of a spoiler. All right. So let's consider a preemptive scheduler. Why? Because the problem is, A, this huge working process is slowing up the works for everybody else. So what do? Can we, with a chainsaw, slice process A up into smaller bits? Or can we, and actually I'm getting way ahead of myself by 2 concepts. So ignore I said that. That comes, slicing things up comes later. What if these smaller processes could interrupt, could butt in and say, hey, dude, I only need that for like a couple minutes, or I'll share with you what happens frequently at office hours. This is exactly what happens at office hours. I get a queue going outside, right? I'm working with a student, and I'll simply ask, all right, does someone have a quick question? And somebody will raise their hand, and I'll handle their question in about a couple seconds, couple of minutes, most. And that person is off and on their way, and the next person moves in. So that's the kind of idea that we want. We want to be able to interrupt the large process to allow the smaller ones time on the CPU. So the previous schedulers, FIFO and SJF are non-preemptive. Once a process is scheduled, it runs to completion. We need a way to butt in. So we introduce shortest time to completion first. And it introduces a new dynamic which says that when a process arrives in the queue, you take a look at the remaining runtime of all the processes in the queue, including the one that's currently on the CPU, and the smallest one gets scheduled next. So, shortest job first, as we've seen before, no preemption, so B and C are stuck waiting on A. STCF, we have a completely different dynamic. Because every time these processes come in, so A runs, right? And it runs for 10 seconds, and then B and C come in. And so we evaluate between B and C who goes next. We run B first, because it goes 10. Then it's done. And once it's done, we evaluate the queue again and run C. And then finally A can finish. And so our turnaround time, is 36.6. So we have the advantages of SJF under the best case scenario, but more uniformly. So we have more uniform performance throughout. All right, so next up is round robin. Any questions so far? So we did FIFO. All right, can someone tell me what FIFO is? First in, first out. Or as I like to call it, ladies' first algorithm. Or as I also like to call it the caveman algorithm. Whenever you're trying to figure out when to do something on a computer, or really any system, I mean, this applies to industrial engineering as well, process engineering. Yes? Yes? I thought I heard professor. Question, okay. Is the idea of first in, first out. That is like the most intuitive, simplest, and this is a pattern that we're going to see through this class. There are intuitive approaches that are simple and even fast to implement, but when the case becomes more complex and more moving parts, it becomes less desirable. And FIFO is one of those. Fantastic for solving an immediate problem, but in the long term, under more complicated cases, falls apart pretty quick. All right, SJF, tell me SJF. Shortest job first. All right, so shortest job first. What's the advantage? Why do we want shortest job first? What's the motivation behind it?
It's also pretty simple to implement, and it's faster than FIFO.
Why? And qualify that.
I mean, overall, it's like the same amount of time, but for the turnaround time for each job is going to be on average lower, because you're not going to get, like with the example, you're not going to get shorter jobs stuck behind a longer job that's getting scheduled for them just because it arrived a millisecond before.
Right, but the reverse can also happen, right?
Yeah.
So you do have a problem. So shortest job first, the intuition behind shortest job first is what we saw with FIFO with a single large job. A single large job and all of your small jobs get screwed. So why not give the small jobs the priority? And by the way, that idea of prioritizing smaller jobs is going to come up again. Because it's not a bad idea. Like, if you have a ton of small jobs, get them out of the queue quick, because generally speaking, short jobs might be interactive jobs, might be jobs that are response time, and we'll talk about that coming up next, that are sensitive to response time. So it's a good idea to get these out first. But that doesn't always work, especially when the big process comes in first anyway. So you're stuck. All right, tell me about STCF. Why are we doing STCF? What's the point?
We can, instead of having to wait until the massive process is finished, we put it on hold and let the small guys go in the middle and then continue it later.
Almost, but not quite. It's not quite right. All right? So, say that again. Actually, say that one more time.
We pause the big guy.
Okay, there you go. That's correct. That's the correct part. Okay. Yes. Now, we have the ability when new processes come in, we can evaluate and say, oh, you're a short process. Let's go ahead and just get you out of the way. Like, hey, do you have a quick question? Let me get you out of the way. Interrupt the big job, like I'm sitting with a student explaining full stack web development. And that student leaves satisfied that the question was answered, and I can get back to the original student until the next short job comes along. All right, so far we have been primarily looking at turnaround time as our primary metric. But as, of course, I've been hinting at, that's not the only metric, because so far these jobs, you can think of them as batch jobs. Like in the old tiny computers, or maybe you're dealing with a supercomputing cluster and you're submitting a large computational workload, right? A batch job that doesn't require interaction. What if your process requires interaction? What if you actually need responsiveness? Imagine you're at the terminal, you want to load VI, but your system, for whatever reason, is running SJF or running STCF. Yeah, you might get on the queue pretty quick, but you might not necessarily get loaded first because there's still a process that's waiting there. Imagine not being able to get a response from VI for several seconds. So that's why we need to measure response time. We need to measure from the time that, effectively you hit return on the command to the time that you get out. Effectively. It's really the time from when it goes into the queue to the time that it first gets on the CPU. All right, so your programming assignment is due 9/16. No. All right, so sometimes we care about when a job starts instead of when it finishes. Why? Because we want that quick responsiveness, especially with interactive. So response time is the first runtime, meaning the first time it gets put on the CPU. So let's say it doesn't get put on the CPU until T5, but it got put in the queue at T0, its response time would be 5 seconds. All right? So response versus turnaround. So remember, turnaround concerns itself with the entire process from beginning to end. From the time that it first enters the ready queue to the time that it terminates. Response time is from the time it enters the ready queue to the first time it is scheduled. So here, B arrives at 10 seconds, which means, so B arrives at 10, but it doesn't run until 20. Response time, 10 seconds. All right, so all the previous schedulers have terrible response times. However, we're going to introduce round robin or the chainsaw scheduler, because we're going to chop those processes into tiny little pieces and schedule them accordingly. So we're going to alternate between ready processes some multiple of your context switch time for reasons that I think we get into a little later. But basically, every time timer's going off, and every single time it does, it triggers the CPU, it triggers the operating system. Who do I schedule next? And you're constantly alternating processes, as we see here. All right? So, we have first in, first out versus round robin. So, which is each? I think that's pretty obvious based on what I told you. So what happens is, so this context switch time, each process, regardless of its runtime, is only allowed to be on the CPU for a fixed amount of time. You've been on the CPU for 2 seconds, you're done, next. You've been on the CPU for 2 seconds, you're done, next. By the way, the timescales are actually much tighter than that. I gotta look up, there's a neat thing that happened in the Linux kernel, I think it was last year, where they changed the timing of that Q value in the schedule, in the kernel itself. And they made it much tighter. So the default, I don't remember what the default was, but the default was, I want to say it was 250 nanoseconds? No, the default was 500 nanoseconds. And it's done that way because the kernel, the default kernel configuration has to be very conservative for stability purposes. Because this kernel has to run on tons of different hardware and an uncountable variety of workloads. So we keep that time slice relatively long. However, in reality, every Linux distribution was setting it to 250 because it works, and it was proven, at least in some common scenarios like desktop, that it was super stable. And after years and years and years, the Linux kernel finally said, you know what? I think we can go with 250 as the build. All right. And if you remind me with an email, I'll send you guys the article on that. And don't be surprised if I got my numbers wrong. All right, so time slice can only get so much time. And this is true for all processes regardless of their length. So we have 3 equivalent processes just like before. But now we're slicing them up. They take the same amount of time, but their response time is radically different. So in this case, A has a response time of 0. It comes in, and it was immediately put on the CPU. Process B has a response time of 1. Process C has a response time of 2, and so on. And read and add those together, add those together, divide by 3 to get 1, versus here in FIFO land, response time of 5. Now, very important to note that even though response time is fantastic under round robin, turnaround time suffers. Because essentially what you're doing, so consider the turnaround time for A. So A comes in at 0 and doesn't exit until 12. B also comes in at 0, but it doesn't exit until 13, and C 14, and so on, right? Because essentially by chopping them up, you're taking all of the processes and expanding them out, spreading them out over time. All right, any questions? Yes?
Is there any amount of time lost doing all that switching, or does it just happen?
Yes, that's an awesome question. That is an awesome, in fact, that's probably for this, best question. That gets my vote of best question. Absolutely it does. And that's why I said, and you probably didn't pick up on it, but I said that the Q value is set to some multiple of the context switch time, typically. Because, so think about it, context switches aren't free, they take time. So if we make the Q value too small, then you're spending more time context switching than you are doing real work. So by making it a multiple of the context switch time, yes, you're doing the context switch, but at least you get to do real work while you're on the CPU. And this is going to come up in actually somewhat larger scales when we talk about I/O. And the idea that there's a trade-off between, so spoiler alert for the I/O section, but it's relevant to this. So when dealing with a device, I can choose to just simply keep asking it in a loop. Are you done yet? Are you done yet? Are you done yet? Are you done yet? Are we there yet? Are we there yet? No! Are we there yet? No! Are we there yet? No! Obviously, this uses a lot of CPU. It's not very optimal in a lot of cases. But what if the device is fast? What if the device is faster than a context switch? Then it might make sense. So normally what we do in that case is, so we go from polling to interrupt. We put the process to sleep, and it waits until the device is done to be reawakened, understanding that you just incurred a context switch. What if we can avoid the context switch? For very fast devices, you can. So what if, are you done yet? No. Are you done yet? Yep, here you go. And you're off to the races in less time than the context switch, you've actually saved time. So context switch is overhead that we need to be mindful of when dealing with these things at a low level. It matters a lot. So great question. Anybody else have a question? All right. So we talked about turnaround time. We talked about response time, and we've covered all of our major schedules. And on Thursday, I'll go through and walk you through, maybe not all focus. FIFO's kind of, like I said, FIFO is caveman algorithm. It shouldn't take you long to figure out turnaround time for FIFO. But STCF, and the same with SJF. SJF is very similar to FIFO, essentially. It's just that if we get processes coming in at the same time, we will prioritize the shorter ones. STCF and round robin are the interesting ones, and the ones that we'll do some examples. All right. Oh yeah. So speaking about devices, so far, our jobs only use the CPU with no I/O. This, of course, is not a realistic case because computers are more than just CPUs and memory. You got peripheral devices that you need glue. And as I've been alluding to all along, devices can come along and interrupt you. Devices can come along and make you wait. How do we deal with CPUs? Or how do we deal with devices? So let's add devices in the mix. All right, not I/O aware. So remember, disk requests take forever, lifetimes at the CPU scale. So A is on the CPU. And then it needs to use the disk, because of course it does. And so it goes to use the disk, and it just sits there, still on the CPU, because the CPU, or the OS, doesn't care, it's not aware of I/O. We just have to sit down and wait for process A to complete the I/O. Meanwhile, poor process B gets to suffer as a result. So what if we could take advantage A runs, makes the disk request, gets put to sleep, B gets put in its place until the request comes back. A now gets to continue running, processing its data, until, oh, it needs to read from the disk again, in which case we put it to sleep, bring B in, and so on. And finally, the runtime of each job is known. This is the hardest one, because so far, we have been taking advantage of a little known superpower that I just gave you, and that you've had for the last couple of weeks, and now I'm taking it away, which is the ability to see into the future. So you know how long each job is going to run, so far. Which is not a realistic expectation at all. The operating system can never know, at least never know precisely. There's all sorts of statistical games, and maybe throw in AI while you're at it, to figure out the estimated length of the process. That all is a possibility. But, by the way, not generally recommended. In fact, let me toss this question out. So, with all of the super awesome AI and neural networks and all of this and statistical predictions, why don't we have a super intelligent process schedule? Okay, complexity.
Maybe because it's just not worth it. Maybe on average it might be faster, but you know, for every once in a while when it decides to schedule something that's going to make one of your processes run a lot longer than it would otherwise in a traditional scheduler.
Yeah, so
It's inconvenient.
that's actually a really good point, and that's a kernel of truth that spans throughout all sorts of algorithmic domains. The idea of, is it worth it? Which is tied to complexity, and those two put together, so there's a missing element. It's not just the complexity, because neural networks by themselves, I'm not talking LLMs, neural networks aren't that complex, but there's a root there.
The time it takes to actually run the calculation.
That's it. The complexity means that it runs for a long time, and all of a sudden it doesn't become worth it. Because remember what I just said not more than 2 minutes ago. So you have a process, and this process is being traded off the CPU in the span of, oh gosh, is it microseconds? You don't have a lot of time to make a decision. And remember back in, I think it was last week's lecture, how many processes were running on my Mac?
500 something.
500 and something. So can you make a super intelligent, super accurate prediction on 500 processes, which each process probably has a different performance profile? Some of them are GUI applications, some of them are background processes, some of them are sleeping processes. All of this complexity, and you're asking me to make a decision in less than 250, what is it? What did I say, microseconds? Or nanoseconds? I don't remember. I genuinely need to look it up. That's not going to happen, at least not right now. Maybe in the future, if we have a 10-fold, 100-fold explosion in processing power, maybe we'll do it then. But for now, and this holds true for a lot of these algorithms, we just don't have the time to be super duper smart about things. We can be fairly clever, for sure. All right. So, the runtime of each job is known. What if it's unknown? What if we don't know? And that's the common case. And now we're actually entering into the land of real schedulers that run, or used to run, sadly, on real operating systems. MLF queue, multi-level feedback queue. So we can afford to be somewhat clever. So, what do we want to do? want to support general purpose scheduling. What this means is, can we support both long jobs and short jobs? Interactive console and GUI users and batch jobs. Can we do so? Can we do both effectively? And also deal with the thorny issue of, okay, at this point, we don't know how long these processes are going to take. So, we want to support interactive programs and improve response time, support batch problems, or batch programs, and deal with turnaround time. So the way that we do this is through multiple levels of round robin. All right, so we're going to start building a set of rules. Rule 1. So all processes have priorities. They belong to a priority queue. So the queues are their priority levels. If the priority of A is greater than the priority of B, A runs. If priority of A equals the priority of B, then run them in round robin. In other words, alternate. So here we see highest priority we have A and B, C, D. All right, so one thing that we need to figure out is how do we set the priority? And by the way, spoiler alert, we're going to use this idea of shifting their priorities as a way to deal with the problem of not knowing how long they're going to run. So approach number 1 is what's called nice. It's you just set it to the lowest possible initially and directly. And approach 2 is do it dynamically based on its history. And we can't really guess. The problem with nice, the problem with directly setting a process's priority is that's a lot of guesswork. It goes back to our initial problem of why don't we use super duper LLMs and AI to do process scheduling, because it would take a lot of computation power to figure out what the proper priority is. So instead, we're going to use a pattern that we're going to see through this class. So you know in those financial investment companies, at the very end they say that past performance is not indicative of future performance. In operating systems, that is not true. Generally, ASCOs. Why ASCOs? Because it's all statistical. Statistically speaking, a process's prior behavior informs what its future behavior could be. And we can make decisions based on its past behavior. We might be wrong sometimes, but the advantages of when we're right far outweigh the pitfalls of being wrong. So, we're going to use history. So, history. We know that processes alternate between I/O and CPU work. We consider each CPU session as its own job. And we guess what a job will be like based on past jobs from the same process. What do we mean? So, we're going to have two more rules. Rule 3, all processes start at top priority. All processes are immediately top dogs in the system and have immediate access to the CPU. Rule 4, if a job uses the whole slice, eats the whole slice of pizza, we devote the process because we believe that it's going to be a little piggy pig and it's potentially going to be a long-running job. So we devote it. So here is what that can look like. All right, process starts to be top priority. It's on the CPU. You just ate an entire slice. Demote it down to Q2. It eats another slice. Demote it down to Q1. It eats another slice. And now it finally gets put at Q0, where, all right, it can live out its remaining life at the lowest priority. Do you have any problems here?
I mean, what happens if you have a heavy job that also requires a lot of computing power?
Okay, yeah, that's a part of it. All right, but what's another
And that's
potential problem?
unnecessary.
If you had a lot to do for a fairly short amount of time, but then it never pops back up if you don't need as much.
Yeah, starvation. So what if you had a lot of short-running processes? It is possible for this long-running process to never see the CPU again. It can get live long. All right, so here you see an interactive process joins, and it's great for the interactive process because it runs and leaves. You know, your interactive session, you're in VI, right? You're just editing code, your keyboard responses are quick and snappy. So it's really great for the response-sensitive processes. Not as great for those processes at the bottom. All right, one of the problems, it's unforgiving. Oh, the other problem, gaming the system. So if you know that, oh, I can't use up an entire time slice, what if right before you think you're going to come up on your time slice, you call yield? So let's say the time slice is 250 nanoseconds. You somehow, because you're a brilliant software engineer, a brilliant OS developer, calculate that your code on this particular architecture, you've got a loop segment that can run for 230 microseconds. Now, you get to stay at the top dog. You just call yield. Next time you're up on the CPU, you're back at the top dog. You run for another 230. Yes.
I was gonna ask why would anyone ever do that? And the first thing that popped into my mind is, isn't the only type of programmer that would do that is someone making malware?
Yeah. Yeah.
Okay.
Yeah. Although, you know what? I have heard some really wacky stories of programmers competing for CPU time back in the day. So certainly not now
I
in
guess like
today's milieu. But back in the day, that would have been a big deal for them because that meant, oh, that means that I get my homework assignment done tonight and I get to go home and see my girlfriend versus that poor sucker's going to be there and he's going to pull an all-nighter. But that was back then and not now. And it's hard to tune, right? Because it's hard to determine exactly when you want to, what you consider to be, too much CPU. So in those, it goes further. There is a neat solution, and it's an interesting solution because there's a pattern in computing where there are certain algorithms that can get stuck in a rut. The general class of problems is called local minima, where either the system thinks it's reached the optimal state. This is true in AI, so you've probably learned about this in machine learning, where you are running the algorithm and you're getting closer and closer and closer to a solution, and all of a sudden your solution stops improving. And from your perspective, it's done. That's it. We've solved it. We've developed, we've developed a little remote control car that can solve the maze. Whatever it might be, you think you got it. But when you look at the entire scope of the problem space, oh no, that was just one small hill, right? You climbed up that hill, Your number isn't improving. Any direction you go from here is only down, it's only worse. So therefore, you must have found the answer. Well, no, there's a taller peak over here that represents the real answer. You've been fed down a false answer. So these are the kinds of ruts that we can run into. And in this case, we can run into a rut wherein we have screwed over all of our long jobs, and all of our long jobs are now live-locked. They can't make any progress. Just like here in AI land, I can't make any progress, because if I look north, my results don't improve, they get worse. If I look east, same thing, west, same thing, south, well, I came from south, that's not gonna be any better, so I'm stuck here. This green process is stuck there. We're also going to learn later in memory. We're going to learn about something called Ellery thrashing. Ellery thrashing is a situation where TLDR, so this is a cache replacement algorithm, where all of a sudden it's nothing but cache miss after cache miss after cache miss after cache miss, and you can't break out of it. Or at least not until that particular loop ends. And each cache miss is disastrous for performance. So how do you get out of this? In this case, one possible solution, actually, let me see if you guys can intuit a solution here. So if we're stuck in a rut, what do you think we can do? What might help the situation? Yes?
And at first, it fixes like this one mistake, maybe you can promote it after a fixed amount of time. And if it does take up too much time to promote it, so like fixed amount of time, something like that.
Oh, so close. So close. So the answer is, well, can we temporarily promote the green process? The answer is yes, but
This is just a question about, MLM.
yeah,
The motion thing, is this per process or per job? Like if I have
per
a long.
job.
Okay, so if I have a long, like, init process, or init job, that doesn't screw over the rest of my process.
Correct.
Okay.
All right, so you started with a great start. That's a great start to the solution. What might we do, because keep in mind, pretend this is a more complex scenario, and we have many more processes running. What might we want to do and get those same results without having to think about, well, how long will this process spend on the CPU? Oh, I think we're raising your hand. You know, but no, it's not stupid at all. You're just overcomplicating it. Because here's the thing. All right, so we know that the system is now in a stuck state. What do you do when something gets stuck? When a machine gets stuck? What do you typically do with that machine? Okay, turn it off or restart it. Gosh, you guys are so digital. Huh? Hit it with a hammer. Yes. So that's how we unstick this. We hit it with a hammer. And what do I mean by hitting it with a hammer? You set all the processes to top priority. You essentially reset the system, right? Because once the default state process comes in, it gets top priority. So now, bang, all the processes jump. They're now all at high priority. And now what we hope to accomplish in doing this, maybe we have some long-running processes that are just this shy of completing. Can we flush them from the system? Can we just get them out of there? And that's what just setting the priority. So, LRU thrashing, similar kind of idea. Now, once you get into LRU thrashing with caching screwed, you might want to think of an alternate approach. So, a reasonable alternative approach to page replacement is, why not just randomly assign them? Instead of trying to be all clever about things, Why don't we just, you go where you go? That does avoid it getting into a rut, because the problem with getting into a rut is the deterministic nature of these algorithms. And we'll learn when we talk about Belody's anomaly and stack algorithms, all of these super deterministic algorithms have a problem in that they can either get stuck in ruts, or worse, with stack algorithms. Get this, we'll get to learn about this in about a month maybe? Would you believe that there are scenarios where increasing your cache size decreases your performance? And that is Belody's algorithm. It's the result of stacking algorithms because their deterministic nature, in a manner of speaking, gets them into a rut. So, here, we want to periodically shake the box, hit it with a hammer, reset everything in the hopes of getting out of that rut that got you from my first. All right, lottery. We have a whopping 20 minutes. I don't actually cover lottery on the exam because lottery kind of gets crazy after a while because the idea is that you're essentially assigning processes time on the CPU, and then later the system grows into